Hello everyone. So we'll continue from where we left off last time. Uh, we are going to apply this particular statement for the balance of linear momentum to this tetrahedron figure. But in order to do that, we'll use the mean value theorem of integration. Okay. So let me go to the next page, but I will I've already copied this figure. Just paste it here, and maybe also reduce the size of this figure a little bit. Okay, I think I'm happy with that. Okay, so because so just taking a brief look at the previous slide, because I want to use this mean value theorem for integration, and you see that in this balance of linear momentum equation, I have both the surface integration as well as the volume integration. First of all, I'll have to use this surface integration thing as well as this volume integration formula. Okay, both these ideas will be necessary when applying this thing. Now, this integration TdS, it can be done by parts over these various surfaces. So these various surfaces mean I have the surface ABC, first of all, this ABC surface, then I have the surface OCB, then I have the surface OAC, and then I have the surface OAB. So I'm going to separate out or decompose this entire integration over the surface into separate parts over these various triangles. Okay. Now, for that, what I will actually need is the value of this area. Okay, the area of this of each of those triangles. So the way that will keep the derivation very neat and clean will be to consider this triangle ABC, and then to write the expressions for the areas of the other triangles, the triangle OCB, the triangle OAC, and the triangle OAB, in terms of the area of the triangle ABC. And that's a very neat idea, and we can do that again by taking advantage of the special tetrahedron figure, because you see the triangle OCB here is nothing but the projection of the triangle ABC on this x2 x3 plane. Similarly, the triangle OAC is nothing but the projection of the triangle ABC on the x1 x3 plane, and the triangle OAB is nothing but the projection of the triangle ABC on the x1 x2 plane. So we are going to exploit this projection idea to write down the values of the various triangles in terms of the triangle ABC. That is the first thing we are going to do. So at the very beginning, you note that this n hat, okay, this n hat is the unit outward normal to the triangle ABC. Now this n hat is a generic unit outward normal vector, but in terms of components, how can it be expressed? So suppose it has the components n1, n2, and n3 along each of OX1, OX2, and OX3. Then can I not write it like n1 e1 hat plus n2 e2 hat plus n3 e3 hat? Can I not write like this? I can, of course, because I know already that along OX1 my unit vector is e1, along OX2 my unit vector is e2, and along OX3 my unit vector is e3. So n1 is the scalar component of n hat along e1, n2 is the scalar component of n hat along e2, and n3 is the scalar component of n vector n hat along e3. Now I'm going to use this this decomposition to write down the projections of the various or the areas of the various triangles in terms of projections. So it's like this. So triangle OCB, that will be equal to triangle ABC times N1. Triangle OAC will be equal to triangle ABC times N2, and triangle OAB will be equal to triangle ABC times N3. Okay. If you are a little bit confused about how this came about, you can simply take not a tetrahedron but a simple right angle triangle and try to consider the sides of the non-hypotenuse sides of the right angle triangle, of the two legs of the right angle triangle, in terms of the projections of the hypotenuse. Okay, so that way you will get some connection between how this is arising and that two-dimensional figure. So we'll proceed with the application of the balance of linear momentum equation. So we take one look again here. So I want to write down this TDS thing as well as I want to write down this thing. Now for the right hand side, okay, I'll write down the right hand side first. Let me do that. Sorry. So first of all, I considered the triangle ABC itself. So for the triangle ABC, the integration TDS, what will that contribute? So let's say that this is some t vector, but now it has to be evaluated at some specific point x star. Okay, it has to be evaluated at some specific point x star within the triangle ABC, and then I have to multiply this by the area of the triangle. Let me take a quick look at this thing. So you see, any integration, so this FR is like this t here, and then this ds is just the ds. So here the integrand evaluated at some specific point within the domain multiplied by the size of the domain, and that is exactly what I have written here. Considering the triangle ABC, the integration is for the t vector with the subscript n, and that I will have to write here. I must write this here. So this is t subscript n. The superscript star denotes that this traction vector is now for a very specific point within this domain ABC. Okay. Next, considering the triangle OCB. For OCB, which is my traction vector? The minus T1. So minus T vector subscript 1. Okay. So let me write this in a better fashion, in a very nice explicit fashion. Because I want to write my surface integration, I'll put the plus, and then I will recognize that the traction vector itself is the minus t vector. So this is minus t vector subscript 1, this entire thing, and then this is multiplied with the triangle OCB. However, this is not yet complete, because I am writing like this by using the mean value theorem of integration, and for that I must put a star here. This is some specific point within the triangle OCB. Now some of you might be thinking, I have written a star here, I have written a star here also. Certainly they are not the same specific points, because you see this star corresponds to some point, some specific point within the triangle ABC, and this star corresponds to some specific point within the triangle OCB. But I don't want to keep on writing different stars on the superscripts. I will run out of symbols and it will be a complete mess of a writing. So I hope you all understand that this star represents some specific point within triangle ABC. This star represents another specific point within the triangle OCB. Okay, I'm not writing different stars for this. Okay, next, for the triangle OAC, it will be minus T, but with the subscript 2. Again, some specific point within the triangle OAC multiplied by the triangle OAC. And finally, for the triangle OAB, it should be minus T vector, subscript 3, superscript star for some specific point within the triangle OAB multiplied by triangle OAB. So the right hand side of this equation, the right hand side of this equation, this is done. Now we are going to write the left hand side. The left hand side, so this is rho dv dt b vector. This entire thing multiplied by the volume of the tetrahedron. Now we don't have to fear, because again we can exploit the nice figure that we have chosen. This is the big advantage of this, another big advantage of considering the tetrahedron, that we can write the entire volume of the tetrahedron OABC as the height of the tetrahedron times the area of the triangle ABC. Okay, so I repeat, the volume of the total tetrahedron OABC is equal to the height of the tetrahedron. So it is basically the perpendicular distance from the point O to the plane ABC multiplied by the triangle ABC together with the factor 1/3. Okay, so this is 1/3 the appropriate height from O measured to the plane ABC and multiplied by the triangle, the area of the triangle ABC. Okay, so the most difficult part of our derivation is actually done. And let us not forget that this entire thing, the rho dv dt minus b, that is actually evaluated at some specific point. So I'm just putting a superscript over the entire thing. Okay, so you understand that is, this star refers to some specific point lying within the entire domain of the volume OABC of the entire tetrahedron. Okay, so this is the most difficult step which you have just done. From now it is quite easy. What we'll do now is we can keep on proceeding like this, but now we'll do one last trick. That last trick is to consider that our tetrahedron, although we have drawn it to be like a finite size thing to make it look very clear, but in reality what we really need is a tetrahedron which is actually infinitesimal in size. I repeat, what we really need is a tetrahedron which is infinitesimal in size, because when we consider such a tetrahedron, basically what is going to happen is that these different specific points that we have seen, they are going to converge to one single point, which is nothing but this point O. This is the trick. Okay, this is a very nice trick. So again I'm saying, when we take this tetrahedron to be very small, so that you can make by taking this height to be very, very small. You keep on reducing the height, the triangle ABC is going to proceed towards the origin. Okay, so it is going to go into towards the origin like that. So take H. Okay, so the triangle ABC, it proceeds or starts moving towards the origin O. Correspondingly, the triangles OCB, the triangle OAC, and the triangle OAB, they also become smaller and smaller, so that in the limit that H actually tends to 0, what will happen is that these various specific points, okay, which are actually different points lying in the different domains, the surface domains, the volume domains, all these things, when the H is tending to 0, what will happen is that for all intents and purposes, that star point is nothing but the point O itself. This is the, I mean, we don't have to write any equation for this mathematical idea, but this is the most sophisticated idea in this entire derivation. Okay, so once this is done, what we can do is, once we take this H tending to 0, we can immediately write that the left hand side will be tending to 0, because you understand that we have the triangle ABC here, and each of these OCBs, OAC, and OAB, they can be written in terms of these things, which we can actually write. So let me write this down here. Okay, so this thing is nothing but triangle ABC times N1. This triangle OAC is nothing but triangle ABC times N2, and this triangle OAB is nothing but triangle ABC times N3. So you see, both on the left hand side and the right hand side, you have the triangle ABC common. So triangle ABC can be cancelled out from both the left hand side and the right hand side. What remains is this H, and you are taking H tends to 0. So should we not have H on the left, 0 on the left hand side? We must have that, and what we are left with is this. So we don't have to write this, we don't have to keep on writing this star, because we understand that all of these things are evaluated at basically at the point 0. So this is just the Tn hat evaluated at the point O minus T vector 1, again evaluated at the point O for all practical purposes, times N1 minus T vector subscript 2 evaluated at the point O times N2. Finally, minus T3 N3. Let me write this down, this important point, that in the limit H tends to 0, all the traction vectors are evaluated effectively at point O. Therefore, what we have is this thing. Our job is almost done. Okay, we just have to write one another step. So this equation I'm going to repeat in the next slide, and then with one more step you will see that what the connection is between the traction and the stress. All right, so let me quickly finish this up. So what I have written earlier is Tn vector is T1 vector n1 plus T2 vector n2 and T3 vector n3. You see, this is a vector equation. Okay, since this is a vector equation, it must have within it embedded three separate equations. What are those separate equations? So first one will be Tn, the first component, T1, the first component, n1, T2, the first component, n2, plus T3, the first component, n3. You please note that I am no longer writing the vectors. Okay, this equation that I have just written is just the first component of this entire vector equation that I have written earlier. Similarly, for the second component, I will have Tn2 is equal to T1 to n1 plus T2 to n2 plus T3 to n3, and finally Tn3, the third component of that first equation, will be T13 n1 plus T2 3 n2 plus T3 3 n3. Now, okay, the final statement. Okay, final step is done. Final statement is this, as simple as this, that these various components, these various scalar components that you're seeing here, T within bracket 1 1, T2 1, T3 1, T2 2, T3 2, all these things, all these various things involving the T, they are themselves nothing but the stress components, as simple as that. So let me repeat, these various things that you are seeing, the various terms, the T subscript 2 1, T subscript 1 2, all these things that you are seeing, they themselves are referred to as the stress components. Okay, so all these things, these equations, they can be rewritten like this: sigma 1 1 n1 plus sigma 2 1 n2 plus sigma T1 n3. Tn2 is equal to sigma 1 2 n1 plus sigma 2 2 n2 plus sigma T2 n3. Tn3 is equal to sigma 1 3 n1 plus sigma 2 3 n2 plus sigma T3 n3. Okay, and all of these things together can be written in short using indicial notation or index notation as sigma ji nj. You can check for yourself by substituting the various values of I and j. First of all, you note that on the left hand side, this n is just a representation of the fact that you are considering the traction vector on a plane which has the unit outward normal as n. So this n itself is not the index, it is the I which is the index. Okay, the I is the index representing the vectorial nature of this entity. So so you have the free index I here, meaning that this is a vector, a tensor of order 1. And on the right hand side also, the entire entity, whatever is written, you see the j index is repeated. So it is not a free index, it's a dummy index. The free index that you have is I. And so in terms of the consistency of the tensor orders also, the right hand side is very much consistent with the left hand side, and the right hand side, whatever it is a tensor of order 1 having only one free index, and therefore this also is a vector quantity. But expressed in terms, if you just look at this one, the sigma ji, that is the stress tensor. Okay, so usually what is written is that this T, the time and again we don't keep on writing this n, we just write it like Ti is equal to sigma ji nj. This perhaps is the most important equation that you can come across in one of the most important equations you can come across in all of continuum mechanics. The traction vector is expressed in terms of the stress components like this. So the sigma, okay, in compact notation it is written like this: the sigma equivalent to, in the index notation, as sigma ij or sigma gi, and we will later on discuss about the fact that sigma ij is indeed equal to sigma gi, but generally it is sigma ij, or if you want to write it like sigma pq, no problem in index notation. So this is a second order tensor, and this is nothing but the stress tensor. And this is how the connection between the traction and the state of stress represented by this second order tensor is established through the unit vector n. Okay, so that original notion that the traction vector is inherently connected to a particular plane under consideration, characterized by the unit outward normal to it, is very much present in this equation also. All right, so we'll proceed from this thing in the next part of the lecture, but I again want to emphasize that this is perhaps one of the most important equations you will come across in this course. Thank you very much.